Whether you're winding down after a long day or just beginning to explore the mysteries that keep you awake with wonder, you're exactly where you need to be. Tonight, we're embarking on a journey to the most extreme world in our solar system, a place so hostile and unforgiving that it makes every other planet seem like a gentle sanctuary by comparison. If you find comfort in these cosmic explorations, I'd be grateful if you'd consider subscribing and giving this video a like. It helps the algorithm connect with more curious souls like yourself, and it would mean the world to me as I work toward building this great community. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination soar to the edges of our solar system. I'd love to know where you're listening from tonight. Drop your location and the time in the comments below. Picture this for a moment. You're standing on the surface of a world where the ground beneath your feet could melt lead in an instant. The sun above you appears 3 times larger than it does from Earth. A blazing furnace that dominates the sky with such intensity that it could blind you instantly. Yet turn away from that sun, and you'd find yourself in shadows cold enough to freeze carbon dioxide solid. This isn't science fiction. This is Mercury, the first planet from our sun. And tonight, we're going to explore why it holds the title as the most extreme world our solar system has to offer. Mercury doesn't just push the boundaries of what we consider habitable, it obliterates them entirely. This small, dense world experiences temperature swings so violent they would shatter any material we know. It endures radiation levels that would kill any Earth organism in seconds. It faces gravitational forces and solar winds that have stripped away any hope of an atmosphere, leaving it naked and exposed to the full fury of space. But here's what makes Mercury truly extraordinary. Despite being the closest planet to the Sun, despite experiencing some of the most brutal conditions imaginable, this little world has secrets that have surprised scientists for decades. It harbors mysteries that challenge everything we thought we knew about planetary formation. It holds clues about the violent early history of our solar system, and it continues to reveal new puzzles with every mission we send its way. Most people think of Mercury as just a scorched, lifeless rock, a cosmic afterthought, the smallest and least interesting of the planets. They couldn't be more wrong. Mercury is a world of extremes that pushes physics to its limits, a natural laboratory where the laws of the universe play out in their most dramatic form. It's a place where a single day lasts longer than an entire year, where ice can exist just meters away from temperatures hot enough to melt zinc, and where the very ground rises and falls like ocean tides under the gravitational pull of the sun. Tonight, we're going to peel back the layers of this remarkable world. We'll discover why Mercury experiences the most extreme temperature variations in the solar system, swinging from over 800 degrees Fahrenheit on its day side to minus 300 degrees Fahrenheit in its polar shadows. We'll explore how this tiny planet generates one of the most unusual magnetic fields ever detected, and why its core makes up an astonishing 75% of its radius, a proportion unlike any other rocky planet we know. We'll journey to Mercury's mysterious polar regions, where NASA's MESSENGER mission discovered something that shouldn't exist. Billions of tons of water ice hiding in permanently shadowed craters on a world that should be completely desiccated. We'll examine the strange hollows that dot Mercury's surface, features so unusual that scientists are still debating how they formed. And we'll uncover why Mercury's orbit behaves in a way that helped prove Einstein's theory of relativity, making this extreme world a cosmic testing ground for our understanding of space and time itself. But Mercury's story isn't just about extremes, it's about resilience, about how a world can endure the most punishing conditions imaginable and still hold on to secrets that could reshape our understanding of planetary science. Every extreme condition on Mercury tells us something fundamental about how planets form, how they evolve, and what happens when worlds venture too close to their parent stars. As we prepare to dive deep into Mercury's mysteries, remember that this isn't just an academic exercise. Understanding Mercury helps us understand the thousands of exoplanets we've discovered orbiting other stars, many of which exist in similarly extreme environments. Mercury serves as our laboratory for studying what happens to rocky worlds in the inner regions of solar systems, providing crucial insights that extend far beyond our own cosmic neighborhood. So settle in as we begin this journey to the most extreme planet in our solar system. We'll start by exploring just how extreme Mercury's environment really is, examining the forces that have shaped this world into the cosmic furnace it is today. Mercury orbits the Sun at an average distance of just 36 million miles. To put that in perspective, Earth sits a comfortable 93 million miles away from our star. But Mercury doesn't just orbit closer to the Sun, it experiences the full, unfiltered fury of solar radiation with an intensity that would instantly vaporize any spacecraft not specifically designed for such extreme conditions. The Sun's energy reaches Mercury with an intensity nearly 7 times greater than what we experience on Earth. Imagine standing under the most intense desert sun you've ever experienced, then multiply that heat by 7. That's just the beginning of what Mercury endures every single day. But the story of Mercury's extremes goes far beyond simple distance from the Sun. Mercury's day-night cycle is unlike anything else in the solar system. While Earth completes one rotation on its axis every 24 hours, Mercury takes 58 Earth days to turn once. But here's where it gets truly bizarre. Mercury completes an entire orbit around the Sun in just 88 Earth days. This means that Mercury's year is shorter than its day, creating a complex dance of light and shadow that produces some of the most extreme temperature variations anywhere in the solar system. During Mercury's long day, when the Sun sits high overhead for Earth months at a time, surface temperatures soar to over 800 degrees Fahrenheit. That's hot enough to melt lead, zinc, and tin. The very rocks beneath your feet would glow red hot, and any water would instantly flash into superheated steam. The surface becomes so hot that it actually glows in the infrared, radiating heat back into space like a giant cosmic furnace. But turn to Mercury's night side, and you encounter the opposite extreme. Without an atmosphere to trap and distribute heat, temperatures plummet to -300 degrees Fahrenheit. This is colder than the surface of Pluto, colder than liquid nitrogen. The same rocks that glowed cherry red just hours before now become brittle enough to shatter like glass. This temperature swing of over 1100 degrees Fahrenheit represents the most extreme thermal variation experienced by any planet in our solar system. To survive on Mercury, you would need technology that could function in conditions that would destroy most materials we know. Your spacecraft would need to withstand thermal expansion and contraction that would tear apart most conventional engineering. But Mercury's extremes don't stop at temperature. The planet's proximity to the Sun subjects it to intense solar wind, a stream of charged particles that flows constantly from our star. On Earth, our thick atmosphere and strong magnetic field protect us from this cosmic hurricane. Mercury has no such protection. Its thin atmosphere, barely detectable and constantly being stripped away and replenished, offers no shield against the solar wind's assault. The solar wind hits Mercury with such force that it actually pushes atoms right off the planet's surface, creating a thin, constantly changing atmosphere composed of sodium, potassium, calcium, and other elements literally blasted from the rocks below. This process, called sputtering, means that Mercury is slowly being eaten away by its proximity to the Sun, one atom at a time. Mercury also experiences tidal forces from the Sun that are 50 times stronger than the tidal forces Earth experiences from the Moon. These gravitational forces actually cause Mercury's solid surface to rise and fall by several feet, like a stone ocean tide. The entire planet flexes and bends under the Sun's gravitational grip, generating heat through friction deep within Mercury's interior. The radiation environment around Mercury is equally extreme. The planet sits within a region of space where solar flares and coronal mass ejections from the Sun arrive with devastating intensity. These bursts of high-energy particles would be lethal to any unprotected life form, delivering radiation doses thousands of times greater than what astronauts experience in Earth orbit. Yet perhaps the most remarkable aspect of Mercury's extreme environment is how it has shaped the planet's very structure. The intense solar heating and cooling cycles have fractured Mercury's surface into a complex network of cliffs and scarps, some stretching for hundreds of miles across the planet's face. These features, called lobate scarps, formed as Mercury's interior cooled and contracted, causing the planet's surface to wrinkle like a raisin. The extreme conditions have also created some of the most unusual geological features in the solar system. Mercury's surface is covered with impact craters, but unlike other planets, many of these craters show signs of unusual erosion and modification by the extreme temperature cycles. Some areas display mysterious hollows, small depressions with bright reflective flaws that scientists believe formed through a process unique to Mercury's environment. As we continue our exploration of this extreme world, we'll discover how these harsh conditions have actually preserved clues about the early solar system, making Mercury a time capsule of cosmic history written in stone and ice. The story of Mercury's formation reads like a cosmic catastrophe. Scientists believe that early in the solar system's history, Mercury may have been a much larger world, perhaps twice its current size. But something violent happened during those chaotic early epochs when planets were still taking shape. The leading theory suggests that a massive impact, perhaps from an object the size of Earth's moon, struck the young Mercury with such devastating force that it stripped away most of the planet's outer layers. This cosmic collision would have vaporized enormous amounts of rock and sent debris flying throughout the inner solar system. What remained was essentially the core of the original planet, wrapped in just a thin shell of rocky material. This explains why Mercury has such an unusual composition compared to other rocky planets. While Earth's core makes up about 17% of our planet's radius, Mercury's core comprises a staggering 75% of its radius. This massive iron core gives Mercury some truly extraordinary properties. Despite being the smallest planet in our solar system, Mercury is surprisingly dense, second only to Earth in terms of density. If you could somehow transport a chunk of Mercury to Earth, it would feel noticeably heavier than an equivalent piece of any other rocky planet. This density comes from that enormous iron core compressed under the weight of the planet above it. But here's where Mercury's story becomes even more intriguing. That massive core isn't just sitting there dormant. It's partially molten, churning and flowing in ways that generate one of the most puzzling magnetic fields in the solar system. Mercury's magnetic field is about 100 times weaker than Earth's, yet it shouldn't exist at all according to many planetary formation models. For a planet to generate a magnetic field through what scientists call a dynamo effect, it typically needs three things: a liquid, electrically conducting core, rotation to create the necessary motion, and convection currents to keep that liquid moving. Mercury rotates so slowly that many scientists thought it couldn't possibly generate enough motion to create a magnetic field. Yet MESSENGER's measurements confirmed that Mercury does indeed have an active magnetic field, suggesting that something unusual is happening deep within that massive core. The magnetic field itself is strangely offset from Mercury's center, tilted and shifted in ways that suggest the core's structure is far more complex than scientists initially imagined. Some researchers propose that Mercury's core might have multiple layers, with different regions solidifying at different rates, creating a complex internal structure unlike any other planet we know. This magnetic field, weak as it is, plays a crucial role in Mercury's extreme environment. It provides just enough protection to prevent the solar wind from completely stripping away the planet's tenuous atmosphere, though it's barely enough to matter. The interaction between Mercury's magnetic field and the intense solar wind creates spectacular aurora displays, though these occur in X-ray wavelengths invisible to human eyes. Mercury's surface tells the story of 4.5 billion years of cosmic bombardment. The planet bears the scars of countless asteroid and comet impacts, creating a landscape that looks like a cosmic battlefield. The largest of these impacts, the Caloris Basin, spans nearly 1,000 miles across and represents one of the largest impact structures in the solar system. The force of this ancient collision was so immense that it sent shockwaves completely through the planet, creating strange hilly terrain on the exact opposite side of Mercury, called chaotic terrain. But Mercury's craters aren't just passive scars from ancient impacts. The extreme temperature cycles have modified these features in ways seen nowhere else in the solar system. The constant expansion and contraction of rock as temperatures swing between blazing hot and freezing cold has created networks of fractures that crisscross the crater floors. Some craters show evidence of materials flowing like thick liquids, possibly from rocks that became so hot they temporarily melted. The most mysterious features on Mercury's surface are the hollows, small depressions with highly reflective floors that appear to be actively forming even today. These features range from a few meters to several kilometers across and often appear in clusters across crater floors and walls. Their bright, almost mirror-like surfaces suggest they're relatively young geological features, possibly still forming under Mercury's extreme conditions. Scientists have proposed several theories for how these hollows form. Some suggest that certain minerals in Mercury's crust become unstable under the intense solar radiation and actually sublimate directly from solid to gas, leaving behind these depressions. Others propose that the extreme temperature cycles cause certain materials to expand and contract so violently that they literally blow themselves apart, creating these unusual features. The discovery of these actively forming geological features was one of the biggest surprises from the Messenger mission. It suggests that Mercury isn't just a dead, inactive world shaped entirely by ancient processes. Instead, it's a dynamic planet where geology continues to unfold under the influence of extreme solar heating. Perhaps even more surprising was Messenger's discovery of water ice in Mercury's polar regions. This finding initially seemed impossible. How could ice exist on a world where daytime temperatures regularly exceed 800 degrees Fahrenheit? The answer lies in one of the most extreme examples of environmental contrast anywhere in the solar system. Mercury's axis is tilted less than 1 degree relative to its orbit around the Sun. This means that the Sun never rises more than a few degrees above the horizon at Mercury's poles. Deep craters near the poles create permanent shadows, where sunlight has never touched the surface since the craters formed billions of years ago. These permanently shadowed regions maintain temperatures around -300 degrees Fahrenheit, cold enough to preserve water ice for geological timescales. Radar observations from Earth and detailed measurements from Messenger revealed that these polar shadows contain billions of tons of nearly pure water ice. Some deposits are several meters thick, representing massive reservoirs of frozen water on a world that should be completely desiccated. These ice deposits likely formed from water-bearing comets that crashed into Mercury over millions of years, with some of the impact debris landing in these permanent cold traps. The contrast is mind-boggling. You could theoretically stand at the boundary between sunlight and shadow on Mercury's polar regions and have 1 foot on ice cold enough to freeze carbon dioxide solid, while the other foot rests on rock hot enough to melt lead. This represents one of the most extreme environmental gradients anywhere in the solar system, with temperature differences of over 1,000 degrees occurring across distances of just a few meters. These polar ice deposits have profound implications for understanding not just Mercury, but the entire inner solar system. They suggest that even the most extreme environments can preserve traces of the water that was delivered to the inner planets during the solar system's violent youth. They also provide a potential resource for future robotic missions to Mercury, offering a source of water for fuel and life support in one of the most challenging environments imaginable. The extreme conditions on Mercury have created a natural laboratory for testing our understanding of planetary physics. Mercury's orbit around the Sun follows a path that deviates slightly from what Newton's laws of gravity predict. This tiny deviation, just 43 arc-seconds per century, was one of the first confirmations of Einstein's theory of general relativity. Mercury's proximity to the Sun means it experiences the curvature of space-time more intensely than any other planet, making it a cosmic testing ground for our most fundamental theories about the nature of space and time. As we continue our journey through Mercury's extreme landscape, we'll discover how this small world continues to surprise scientists with each new observation, revealing secrets about planetary formation that extend far beyond our solar system to the thousands of worlds we've discovered orbiting other stars. The more we study Mercury, the more we realize that this extreme world holds keys to understanding planetary formation throughout the universe. Every measurement, every observation from this scorched and frozen world teaches us something fundamental about how rocky planets evolve when they venture too close to their parent stars. Mercury serves as our natural laboratory for studying the thousands of exoplanets we've discovered in similar extreme environments around other stars. Consider the sheer violence that Mercury endures every single day. As it hurtles through its elliptical orbit, the planet's distance from the Sun varies dramatically, creating even more extreme conditions than its already punishing baseline. At its closest approach, called perihelion, Mercury sits just 29 million miles from the Sun. At its farthest point, aphelion, it retreats to 43 million miles away. This 14 million mile difference creates seasonal variations that dwarf anything we experience on Earth. During Mercury's closest approach to the Sun, solar radiation increases by nearly 50% compared to its farthest point. Imagine if Earth's summer was 50% hotter than winter, not just a matter of degrees, but a fundamental change in the intensity of energy bombarding the planet's surface. On Mercury, this variation pushes daytime temperatures even higher during perihelion, creating surface conditions so extreme that some minerals literally begin to break down at the atomic level. The gravitational forces during these close approaches are equally dramatic. Mercury experiences tidal forces that flex and bend the planet's solid interior, generating heat through friction deep within its core. This tidal heating contributes to keeping portions of Mercury's massive iron core molten, helping to sustain the planet's mysterious magnetic field despite its slow rotation. But Mercury's extremes extend beyond heat and cold, beyond radiation and gravity. The planet experiences some of the most intense micrometeorite bombardment in the solar system. These tiny particles, ranging from dust grains to small pebbles, constantly rain down on Mercury's surface at velocities that would make them deadly projectiles. Without an atmosphere to burn up these cosmic bullets, they strike Mercury's surface with their full cosmic velocity, some traveling at speeds exceeding 100,000 miles per hour. This constant bombardment shapes Mercury's landscape in subtle but important ways. The impacts create a fine dust layer that covers much of the planet's surface, while larger impacts continue to excavate new craters and modify existing ones. The cumulative effect is a world where the surface is constantly being recycled and renewed, albeit at an almost imperceptibly slow pace by human standards. Mercury's extreme environment also creates unique chemical processes that occur nowhere else in the solar system. The intense solar radiation breaks down minerals in ways that simply don't happen on other worlds. Certain compounds that are stable on Earth or Mars become unstable on Mercury, decomposing under the relentless solar assault. This process releases elements like sodium and potassium into Mercury's tenuous atmosphere, creating the thin envelope of gases that constantly streams away from the planet into space. The planet's surface composition reflects this extreme environment. Spectroscopic analysis reveals that Mercury's crust contains unusually high concentrations of volatile elements, materials that should have been boiled away long ago by the intense solar heating. This suggests that Mercury's surface has been repeatedly resurfaced by volcanic activity or impact processes that bring fresh material up from the interior. Material that has been protected from direct solar radiation. Some of the most extreme conditions on Mercury occur during what scientists call thermal anomalies. These are regions where the planet's already extreme temperature variations become even more pronounced due to local topography or surface composition. Crater rims that face the sun directly can reach temperatures exceeding 900 degrees Fahrenheit, while nearby shadows plunge to temperatures approaching absolute zero. These thermal anomalies create microclimates of extreme contrast that exist nowhere else in the solar system. Within a single crater, you might find surface temperatures varying by more than 1200 degrees across distances of just a few hundred meters. The thermal stress this creates is so intense that rocks literally crack and shatter from the expansion and contraction cycles. Mercury's extreme radiation environment extends far beyond visible light. The planet sits within the Sun's corona during solar maximum periods, when solar activity reaches its peak. During these times, Mercury experiences radiation levels that would be instantly lethal to any known form of life. The planet receives doses of high-energy particles that are millions of times more intense than the most dangerous radiation environments on Earth. Yet even in this hostile radiation environment, Mercury has developed its own unique atmospheric phenomena. The interaction between solar wind particles and Mercury's tenuous atmosphere creates processes that exist nowhere else in the solar system. Charged particles from the Sun slam into atoms in Mercury's thin atmosphere with such energy that they create exotic chemical reactions, forming compounds that exist only in the most extreme space environments. The planet's magnetic field, weak though it is, creates additional complexity in this extreme environment. Solar wind particles become trapped and accelerated by Mercury's magnetic field lines, creating radiation belts similar to Earth's Van Allen belts, but far more intense. These radiation belts pulse and vary with Mercury's eccentric orbit, creating a constantly changing radiation environment that adds another layer of extremes to an already punishing world. Mercury's surface geology tells a story of extremes written in rock and metal. The planet's crust shows evidence of having been completely melted and reformed multiple times throughout its history. Some regions display what scientists call ghost craters, circular features that were once impact craters, but have been so modified by extreme heating and cooling that they're barely recognizable as their original forms. The most recent surprise for Mercury came when scientists realized that the planet's extreme environment might actually be creating new types of minerals. The combination of intense solar radiation, extreme temperature cycling, and constant micrometeorite bombardment creates conditions that don't exist anywhere else in the solar system. Under these conditions, familiar minerals might transform into new crystalline structures, creating materials that exist only on Mercury. These extreme conditions have also preserved evidence of the solar system's violent past in ways that more hospitable worlds cannot. Mercury's surface contains impact glass formed during asteroid and comet collisions, glass that has been preserved for billions of years by the planet's lack of weathering processes. This impact glass contains chemical signatures from the impacting objects, providing a record of the materials that were flying around the inner solar system during its chaotic youth. The extreme temperature cycles on Mercury create another unique preservation mechanism. Certain chemical compounds become sealed within mineral structures during the cold polar night, then are slowly released during the scorching day in a cycle that has continued for billions of years. This process creates a kind of geological memory that records changes in the solar system's environment over cosmic timescales. Perhaps most remarkably, Mercury's extreme environment continues to evolve. Recent observations suggest that the planet's magnetic field is weakening over time, possibly due to the gradual solidification of its core. As this happens, Mercury becomes even more vulnerable to solar wind erosion, potentially accelerating the loss of its already tenuous atmosphere. The planet's orbital dynamics are also slowly changing due to tidal interactions with the Sun. Over millions of years, these forces will continue to modify Mercury's rotation and orbital characteristics, potentially creating even more extreme conditions in the distant future. Mercury represents a world caught in a slow-motion transformation, driven by the relentless forces of its extreme environment. Understanding Mercury's extremes has profound implications for astrobiology and the search for life elsewhere in the universe. While Mercury itself is far too extreme to support any known form of life, studying how this world functions under such harsh conditions helps scientists understand the boundaries of what's possible for rocky planets. Many of the exoplanets we've discovered orbit much closer to their stars than Mercury does to ours, experiencing even more extreme conditions. Mercury serves as our closest analogue for these distant worlds, providing crucial insights into how planetary atmospheres behave under intense stellar radiation, how magnetic fields function in extreme environments, and how rocky surfaces respond to temperature extremes that push the boundaries of physics. Every extreme condition we document on Mercury helps us better interpret observations of similar worlds around other stars. As we prepare to delve deeper into Mercury's most extraordinary features, remember that we're not just exploring a distant world. We're examining the limits of planetary physics, the boundaries of what's possible when matter and energy interact under the most extreme conditions nature can create. Mercury doesn't just hold the record for temperature extremes in our solar system. It represents a cosmic laboratory where the fundamental forces of the universe play out in their most dramatic and revealing forms. In the next part of our journey, we'll explore the specific mechanisms that drive Mercury's extreme temperature variations, examining how this small world creates some of the most dramatic climate contrasts anywhere in the known universe. We'll discover how Mercury's unique orbital characteristics create a complex dance of heating and cooling that produces environmental conditions so extreme they challenge our understanding of planetary science itself. The dance between Mercury and the Sun creates a thermal symphony unlike anything else in our solar system. To truly understand just how extreme this world becomes, we need to examine the intricate mechanics that drive its temperature variations. This isn't simply a matter of being closer to the Sun. Mercury's relationship with our star involves a complex interplay of orbital mechanics, rotational dynamics, and thermal physics that produces conditions so extreme they seem to defy the laws of planetary science. Mercury's orbit isn't a perfect circle. Instead, it follows a highly elliptical path that brings the planet dramatically closer to and farther from the Sun throughout its 88 Earth-day year. This orbital eccentricity, combined with Mercury's peculiar rotational period, creates what scientists call a resonance lock. For every 2 orbits around the Sun, Mercury completes exactly 3 rotations on its axis. This 3-to-2 spin-orbit resonance produces one of the most unusual day-night cycles imaginable. During Mercury's long day, the Sun doesn't simply rise and set as it does on Earth. Instead, it performs an elaborate celestial ballet across Mercury's sky. At certain locations on Mercury's surface, the Sun actually appears to reverse direction during its journey across the sky, rising partway, setting again, then rising once more, before finally completing its trek overhead. This solar choreography occurs because Mercury's orbital speed varies dramatically as it swings closer to and farther from the Sun, sometimes outpacing the planet's rotation and creating the illusion of solar backtracking. This complex dance means that some regions of Mercury receive prolonged exposure to direct solar radiation. Certain areas experience what scientists call hot poles, locations where the Sun lingers near the zenith for extended periods during Mercury's closest approach to the Sun. These hot poles become the most extreme thermal environments in the solar system, reaching temperatures that exceed the melting point of many metals found on Earth. The thermal physics at play on Mercury's surface reveal just how extreme conditions can become. Without an atmosphere to distribute heat, surface temperatures respond almost instantaneously to changes in solar radiation. When the Sun rises over Mercury's horizon, surface temperatures begin climbing at rates that would seem impossible on Earth. In some regions, temperatures can increase by several hundred degrees in just a few hours as the intense solar radiation strikes the planet's surface. The thermal conductivity of Mercury's surface materials plays a crucial role in creating these extreme conditions. The planet's surface consists largely of rocky regolith, pulverized by billions of years of meteorite impacts. This powdery material acts as an excellent thermal insulator, preventing heat from penetrating deep into the planet's interior. Instead, thermal energy remains concentrated in a thin surface layer, just a few centimeters thick, creating surface temperatures that far exceed what would occur if heat could efficiently conduct into the planet's interior. During Mercury's day, this thermal isolation creates surface conditions so extreme that they begin to affect the planet's geology in real time. The intense heating causes surface rocks to expand rapidly, while the underlying material remains relatively cool. This thermal gradient creates enormous stress within the rocky surface, literally tearing apart the planet's crust through thermal shock. The constant expansion and contraction cycles have created networks of fractures that extend deep into Mercury's surface, creating a landscape that's constantly being reshaped by thermal stress. But the extremes don't end with heating. When Mercury's long night finally arrives, the absence of any atmosphere means that surface heat radiates directly into the vacuum of space with no mechanism for retention. The same thermal isolation that creates such intense daytime heating now works in reverse, allowing surface temperatures to plummet at rates that would be catastrophic on any world with weather systems. The cooling process on Mercury occurs so rapidly that it creates its own unique geological phenomena. As surface rocks contract during the frigid night, they can actually fracture differently than they did during the heating cycle. Some regions develop what scientists call thermal polygons, geometric patterns of cracks that form as the surface contracts uniformly in all directions. These features create landscapes that look almost artificially patterned, as if designed by some cosmic architect rather than formed by natural processes. The interaction between Mercury's extreme temperatures and its surface composition has revealed surprising details about the planet's chemical makeup. Spectroscopic analysis from orbiting spacecraft has detected the presence of numerous volatile elements that shouldn't exist on such a hot world. Elements like sulfur, sodium, and potassium appear in concentrations that suggest they're being continuously replenished through some active process. Scientists now believe that Mercury's extreme thermal cycles actually drive a form of geological recycling unlike anything seen elsewhere in the solar system. The intense heating during the day causes certain minerals to break down and release volatile elements, which then escape into the planet's tenuous atmosphere. During the frigid night, some of these elements condense back onto the surface, creating a slow but continuous cycle of chemical exchange between the planet's surface and its gossamer-thin atmosphere. This thermal cycling has created one of the most chemically active surfaces in the solar system, despite Mercury's reputation as a geologically dead world. The constant heating and cooling drives chemical reactions that modify the planet's surface composition on timescales much faster than typical geological processes. Some regions show evidence of having their surface chemistry completely altered by thermal processing over periods of just millions of years. A blink of an eye in geological terms. The extreme thermal environment has also created unique opportunities for studying planetary physics. Mercury's surface serves as a natural laboratory for understanding how materials behave under temperature extremes that we can barely recreate in Earth-based laboratories. The temperature variations are so extreme that they push common minerals into phase transitions, creating new crystalline structures that exist only under Mercury's unique conditions. Recent computer models of Mercury's thermal environment have revealed even more surprising details about the planet's extreme nature. The models show that certain regions experience temperature variations so rapid and extreme that they create acoustic waves within the planet's crust. These thermal shock waves propagate through Mercury's interior, potentially contributing to the planet's ongoing geological activity and helping to explain some of the unusual surface features observed by visiting spacecraft. The thermal extremes also create unique electromagnetic phenomena. The rapid heating and cooling of Mercury's surface generates thermoelectric currents as different minerals expand and contract at different rates. These electrical currents interact with Mercury's magnetic field to create electromagnetic effects that exist nowhere else in the solar system. Some scientists speculate that these thermoelectric phenomena might contribute to the unusual properties of Mercury's magnetic field, adding another layer of complexity to an already mysterious planetary characteristic. Mercury's polar regions present perhaps the most extreme example of thermal contrast anywhere in the known universe. The permanently shadowed craters near Mercury's poles maintain temperatures approaching absolute zero, while areas just a few kilometers away experience some of the hottest surface temperatures in the solar system. This proximity of extreme cold and extreme heat creates thermal gradients so steep that they challenge our understanding of heat transfer physics. Within these polar regions, scientists have discovered evidence of sublimation processes occurring at the boundaries between light and shadow. The extreme temperature differences cause water ice and other frozen materials to transition directly from solid to vapor without passing through a liquid phase. This sublimation creates ghostly plumes of vapor that briefly exist before dissipating into the vacuum of space, adding yet another dynamic element to Mercury's already complex atmospheric system. The thermal extremes at Mercury's poles also drive convection processes within the ice deposits themselves. Temperature differences within the permanently shadowed regions create slow circulation patterns as slightly warmer ice rises and cooler ice sinks. These convection currents help to preserve the ice over geological timescales, while also slowly modifying the structure and composition of the deposits. Perhaps most remarkably, Mercury's extreme thermal environment continues to evolve as the planet's orbit slowly changes over cosmic timescales. Gravitational interactions with other planets gradually modify Mercury's orbital characteristics, altering the planet's distance from the Sun and the intensity of its thermal cycles. Over millions of years, these orbital changes will create new patterns of heating and cooling, potentially exposing currently protected regions to extreme temperatures, while creating new cold traps in other areas. The study of Mercury's thermal extremes has profound implications for understanding planetary habitability throughout the universe. Many of the rocky exoplanets we've discovered orbit much closer to their host stars than Mercury does to the Sun, experiencing even more intense thermal cycling. By understanding how Mercury's surface and interior respond to extreme temperature variations, scientists can better predict the conditions on these distant worlds and assess their potential for hosting atmospheric systems or even primitive forms of life. Mercury's thermal story also provides crucial insights into the early history of our own solar system. During the solar system's youth, when the Sun was less stable and more variable in its energy output, all the inner planets may have experienced thermal extremes similar to what Mercury endures today. Understanding how Mercury's geology and chemistry respond to such conditions helps scientists reconstruct the environmental history of Earth, Venus, and Mars during their formative epochs. The extreme thermal environment has also shaped Mercury's interaction with the solar wind in ways that create additional layers of complexity. The temperature differences between Mercury's day and night sides create pressure gradients in the planet's tenuous atmosphere that interact with charged particles from the solar wind. These interactions create plasma phenomena that exist only around Mercury, adding electromagnetic effects to the already impressive list of extremes that characterize this remarkable world. As we continue our exploration of Mercury's extraordinary nature, we'll discover how these thermal extremes interact with the planet's other unusual characteristics to create a world that challenges every assumption we might have about planetary behavior. Mercury doesn't just experience the most extreme temperatures in the solar system. It demonstrates how extreme conditions can drive planetary processes that exist nowhere else in the known universe, making it a cosmic laboratory for understanding the limits of what's possible when matter and energy interact under the most challenging conditions nature can create. The thermal story of Mercury serves as a bridge to understanding the planet's other remarkable features, from its mysteriously large core to its unexpected magnetic field, from its ancient impact scars to its actively forming geological features. Each extreme characteristic builds upon the others to create a world that represents the ultimate expression of planetary physics, pushed to its absolute limits. Limits. Deep within Mercury's core lies one of the most profound mysteries in planetary science. The heart of this extreme world contains secrets that challenge everything we thought we understood about how small planets should behave. While Mercury's surface endures the most extreme temperature variations in the solar system, its interior harbors an even more extraordinary story, one written in liquid iron and magnetic fields that shouldn't exist. To understand just how unusual Mercury's interior truly is, we need to compare it to other rocky worlds. Earth's core makes up about 17% of our planet's radius. Mars has a core that comprises roughly 20% of its radius. Venus, similar in size to Earth, likely has a comparable core-to-planet ratio. But Mercury shatters these expectations entirely. Its core extends to roughly 75% of the planet's radius, creating an internal structure so unusual that it demands explanation. This massive core isn't just remarkable for its size, it's partially molten, churning with convection currents that generate heat and movement deep within the planet's interior. For a world as small as Mercury, maintaining a liquid core should be virtually impossible. Small planets cool rapidly, solidifying their interiors within a few 100 million years of formation. Yet here is Mercury, 4.5 billion years old, still maintaining enough internal heat to keep portions of its enormous core in a molten state. The implications of this active core extend far beyond simple planetary physics. That churning liquid iron generates Mercury's magnetic field, a phenomenon that surprised scientists when it was first detected. Mercury rotates so slowly that conventional planetary science suggested it couldn't possibly generate enough motion to create a magnetic dynamo. A planet needs rapid rotation to create the complex fluid motions that twist and amplify magnetic fields. Mercury takes 58 Earth days to complete one rotation, a pace so leisurely that it seemed incompatible with magnetic field generation. Yet Messenger's magnetometer detected clear evidence of an active magnetic field surrounding Mercury. This field is roughly 100 times weaker than Earth's, but its very existence represents a puzzle that has forced scientists to reconsider their understanding of planetary magnetic fields. The field's structure adds even more mystery to the story. Unlike Earth's relatively symmetric magnetic field, Mercury's field is offset and tilted, suggesting that the processes generating it are fundamentally different from those operating within our own planet. Recent computer models propose that Mercury's core might have a complex layered structure that enables magnetic field generation despite the planet's slow rotation. The outer portions of the core might be liquid while inner regions remain solid, creating interfaces where different types of fluid motion can occur. These models suggest that thermal convection driven by the cooling of the core, combined with compositional convection, caused by the gradual solidification of iron alloys, might create just enough motion to sustain a weak but persistent magnetic field. The magnetic field itself plays a crucial role in Mercury's extreme environment. While far too weak to provide meaningful protection from solar radiation, it does create a small magnetosphere that interacts with the solar wind in fascinating ways. This interaction accelerates charged particles from the solar wind, creating radiation belts around Mercury that pulse and vary with the planet's eccentric orbit. During Mercury's closest approaches to the Sun, these radiation belts become compressed and intensified, creating some of the most extreme radiation environments anywhere in the solar system. The magnetic field also influences Mercury's tenuous atmosphere in subtle but important ways. Charged particles trapped by the magnetic field occasionally spiral down into Mercury's upper atmosphere, where they collide with atoms and molecules to create aurora displays. These auroras occur in X-ray wavelengths invisible to human eyes, but they represent one of the most energetic atmospheric phenomena in the solar system. The energy released during these X-ray auroras is so intense that it actually contributes to the ongoing erosion of Mercury's atmosphere, adding yet another extreme process to the planet's already impressive collection. Mercury's core composition adds another layer of mystery to its extreme nature. The core appears to be unusually rich in iron compared to other rocky planets, with relatively low concentrations of lighter elements like sulfur that typically alloy with iron in planetary cores. This composition suggests that Mercury formed under unusual conditions or experienced some catastrophic event that altered its original makeup. The high iron content contributes to Mercury's surprising density and helps explain why such a small planet can maintain partially molten core conditions. The thermal evolution of Mercury's core reveals additional extreme characteristics. Computer models indicate that the core has been cooling and solidifying from the outside inward over billions of years. But this process occurs much more slowly than it should for a planet of Mercury's size. The extreme tidal heating caused by Mercury's eccentric orbit and the Sun's powerful gravitational field continuously adds energy to the core, helping to maintain its partially molten state long after it should have completely solidified. This tidal heating creates internal temperature gradients within Mercury's core that drive complex convection patterns. Hot material rises from the deep interior, while cooler material sinks, creating circulation patterns that help distribute heat throughout the core. These convection currents also contribute to the magnetic field generation process, creating the complex fluid motions necessary to sustain Mercury's magnetic dynamo despite the planet's slow rotation. The interaction between Mercury's core and its extreme surface environment creates feedback loops that exist nowhere else in the solar system. The massive core generates significant internal heat through radioactive decay and tidal friction, contributing to volcanic processes that have resurfaced portions of Mercury's crust multiple times throughout its history. This internal heat also drives the chemical processes that release volatile elements into Mercury's atmosphere, creating the thin envelope of gases that constantly streams away from the planet. Recent analysis of data from the MESSENGER mission has revealed that Mercury's core might be stratified, with different layers having distinct compositions and physical properties. The outermost liquid layer might be relatively iron-poor compared to deeper regions, while the solid inner core could be nearly pure iron. This stratification would create additional complexity in the core's thermal and magnetic behavior, potentially explaining some of the unusual characteristics observed in Mercury's magnetic field. The core's influence extends to Mercury's surface geology in ways that create some of the planet's most extreme features. As the core cools and contracts over geological time, it causes the entire planet to shrink slightly. This global contraction has created enormous cliff systems called lobate scarps that stretch for hundreds of miles across Mercury's surface. These cliffs represent some of the most dramatic topographic features in the solar system, with vertical relief that can exceed several kilometers. The formation of these scarps involves forces so immense that they literally tear apart Mercury's crust, creating fault systems that extend deep into the planet's interior. The stress fields created by global contraction interact with Mercury's extreme thermal cycling to create complex patterns of surface deformation. Some regions experience compression, while others undergo extension, creating a patchwork of geological features that record the ongoing evolution of Mercury's internal structure. Mercury's core also influences the planet's relationship with the solar wind in ways that create additional extreme conditions. The magnetic field generated by the core deflects some solar wind particles, but many others penetrate the weak magnetosphere and interact directly with Mercury's surface. This interaction creates a complex dance of charged particles that constantly bombards the planet, contributing to the ongoing erosion and chemical modification of the surface. The core's magnetic field also creates what scientists call magnetic reconnection events, where magnetic field lines from Mercury's magnetosphere interact with the solar wind's magnetic field. These reconnection events release enormous amounts of energy in brief, violent bursts that accelerate particles to extremely high velocities. The energy released during these events can be equivalent to millions of lightning bolts occurring simultaneously, creating some of the most energetic phenomena in the inner solar system. Perhaps most remarkably, Mercury's core appears to be evolving in real time. Magnetic field measurements from MESSENGER suggest that the field strength is slowly decreasing, possibly indicating that the core is gradually solidifying as the planet continues to cool. This evolution occurs on timescales of millions of years, but it represents an ongoing transformation that will eventually alter Mercury's extreme characteristics in fundamental ways. The study of Mercury's core has profound implications for understanding planetary formation throughout the universe. Many of the rocky exoplanets we've discovered are similar in size to Mercury, but orbit much closer to their host stars. Understanding how Mercury's core behaves under extreme conditions helps scientists predict what might happen to the interiors of these distant worlds as they endure even more intense stellar radiation and tidal heating. Mercury's core also serves as a natural laboratory for studying the physics of liquid metals under extreme conditions. The pressures and temperatures within Mercury's core create conditions that are difficult to replicate in Earth-based laboratories, providing unique insights into how iron behaves under the extreme conditions that exist within rocky planets. These insights help scientists understand not only Mercury's evolution, but also the internal dynamics of larger rocky worlds like Earth and Venus. The magnetic field generated by Mercury's core has been used to test fundamental theories about how planetary magnetic fields form and evolve. The unusual characteristics of Mercury's field, including its offset and tilted nature, have led to new theoretical models that expand our understanding of magnetic dynamo processes. These models help explain not only Mercury's magnetic field, but also the magnetic behavior of other planets and even magnetic field generation in stars. As Mercury continues its journey around the Sun, its core remains one of the most active and dynamic components of this extreme world. The ongoing evolution of the core drives geological processes, influences atmospheric dynamics, and creates magnetic phenomena that exist nowhere else in the solar system. Understanding Mercury's core is crucial for comprehending how this remarkable planet maintains its extreme characteristics while continuing to surprise scientists with new discoveries about the limits of planetary physics. The story of Mercury's core connects directly to the planet's surface features, many of which bear the signatures of internal processes driven by that massive iron heart. From the global cliff systems created by core contraction to the volcanic plains resurfaced by core-driven heat, Mercury's exterior reflects the extreme conditions that persist within its interior. This intimate connection between internal dynamics and surface features creates a world where extreme processes operate on every scale, from the atomic level to planetary-wide phenomena. As we continue our exploration of Mercury's extraordinary nature, we'll discover how the planet's core interacts with its other extreme characteristics to create surface features unlike anything found elsewhere in the solar system. The combination of extreme temperatures, intense radiation, and internal geological forces has sculpted a landscape that serves as a testament to the power of planetary physics, operating under the most challenging conditions imaginable. Mercury's surface reveals the story of 4.5 billion years written in stone and metal, a narrative of extremes that continues to unfold with each new observation. The planet's exterior serves as a canvas where internal forces, external bombardment, and thermal cycling have created artistic masterpieces of geological complexity. Every crater, every cliff, every mysterious hollow tells part of the story of how extreme conditions shape planetary surfaces in ways that challenge our understanding of geological processes. The most immediately striking features of Mercury's surface are its impact craters, which preserve a record of the solar system's violent past in exquisite detail. These craters range from tiny pits barely visible in the highest resolution images to enormous basins that span nearly a quarter of the planet's surface. The largest of these impact structures, the Caloris Basin, represents one of the most extreme impact events recorded anywhere in the solar system. This ancient collision involved an asteroid or comet perhaps 60 miles across, striking Mercury with such devastating force that it sent shockwaves completely through the planet. The Caloris impact was so violent that it created what scientists call antipodal effects, geological features that formed on the exact opposite side of the planet from the impact site. The seismic waves from the collision traveled through Mercury's interior, converged on the far side of the planet, and literally shattered the surface to create a landscape of jumbled hills and valleys called chaotic terrain. This represents one of the most extreme examples of how a single impact event can affect an entire planet, creating geological features thousands of miles away from the original collision site. But Mercury's craters aren't simply passive records of ancient impacts. The planet's extreme thermal environment has modified these features in ways that exist nowhere else in the solar system. The constant expansion and contraction of surface materials as temperatures swing between extremes has created networks of fractures that crisscross crater floors and walls. Some craters show evidence of materials flowing like thick liquids, possibly representing rocks that became so hot during Mercury's intense day that they temporarily approached their melting point. The thermal modification of impact craters has revealed surprising details about Mercury's surface composition. Spectroscopic analysis shows that many crater floors contain materials with different thermal properties than the surrounding terrain, suggesting that the extreme temperature cycles have sorted surface materials based on their thermal behavior. Dark materials that absorb solar radiation efficiently tend to accumulate in areas that receive prolonged solar exposure, while lighter-colored materials concentrate in regions that experience more moderate temperatures. Mercury's surface also displays some of the most unusual geological features found anywhere in the solar system. The mysterious hollows that dot the planet's surface appear to be actively forming even today, creating bright depressions that stand out dramatically against the darker background terrain. These features range from small pits just a few meters across to complex systems of interconnected depressions that span several kilometers. Their bright, highly reflective surfaces suggest they're among the youngest geological features on Mercury, possibly forming through processes that are still active. Scientists have proposed several theories for how these hollows form, each involving Mercury's extreme environment in different ways. Some researchers suggest that the intense solar radiation causes certain minerals in Mercury's crust to become unstable and sublimate directly from solid to gas, leaving behind these characteristic depressions. The extreme ultraviolet radiation and high-energy particle bombardment that Mercury experiences could break down mineral crystal structures in ways that don't occur on other planets. Another theory proposes that Mercury's extreme temperature cycles cause certain materials to undergo repeated phase transitions that gradually weaken the surface structure. As materials heat and cool through multiple thermal cycles, they might develop internal stress fractures that eventually cause portions of the surface to collapse or blow away. The fact that many hollows appear to be associated with impact craters suggests that the shock from ancient impacts might have created materials that are particularly susceptible to thermal breakdown. The distribution of hollows across Mercury's surface provides clues about their formation mechanism. They tend to cluster in regions that experience the most extreme temperature variations, particularly areas that receive prolonged solar exposure during Mercury's closest approaches to the Sun. This correlation suggests that the formation process requires the most extreme thermal conditions that Mercury can provide, making these features unique to the planet's harsh environment. Mercury's surface also contains extensive volcanic plains that record a period of intense geological activity early in the planet's history. These smooth plains, which cover roughly 40% of Mercury's surface, formed when massive volumes of lava erupted from the planet's interior and flooded low-lying regions. The extreme thermal environment has preserved these volcanic features in remarkable detail, creating a landscape that appears almost frozen in time from billions of years ago. The volcanic plains reveal that Mercury's interior was once far more active than its current state suggests. The volume of lava required to create these features represents an enormous output of internal heat, suggesting that Mercury's core was much hotter in the past. The extreme surface conditions have prevented weathering processes from significantly modifying these ancient volcanic landscapes, allowing scientists to study pristine examples of early planetary volcanism. Recent analysis of Mercury's volcanic plains has revealed evidence of explosive volcanism, unlike anything seen on other terrestrial planets. Some regions show deposits that appear to have formed from pyroclastic eruptions, where volcanic gases expanded explosively and scattered fine particles across vast areas. These explosive eruptions would have been particularly dramatic on Mercury, due to the planet's low gravity and lack of atmosphere, allowing volcanic debris to travel much farther than it could on Earth or Mars. The interaction between Mercury's volcanic activity and its extreme thermal environment created unique geological processes. Lava flows that erupted onto Mercury's surface would have experienced rapid cooling in shadowed regions and extreme heating in areas exposed to direct sunlight. This differential cooling could have created unusual flow patterns and surface textures that exist nowhere else in the solar system. Mercury's surface composition adds another layer of extreme characteristics to this remarkable world. The planet's crust contains unusually high concentrations of certain elements that should have been depleted by billions of years of thermal processing. Elements like sulfur, which should vaporize readily under Mercury's extreme conditions, appear in concentrations that suggest ongoing replenishment through geological processes. The discovery of these volatile elements led to the recognition that Mercury's surface undergoes active chemical recycling driven by the extreme thermal environment. During the intense heat of Mercury's day, certain minerals break down and release volatile elements into the tenuous atmosphere. These elements can travel significant distances before condensing back onto the surface during the frigid night, creating a slow but continuous redistribution of surface materials. This chemical recycling process has created compositional variations across Mercury's surface that reflect the planet's complex thermal environment. Regions that experience the most extreme heating show evidence of volatile depletion, while areas that remain in permanent shadow have accumulated unusually high concentrations of these same materials. The result is a planetary surface with chemical gradients that directly reflect the extreme temperature variations that define Mercury's environment. The extreme conditions on Mercury's surface have also preserved unique records of the solar system's early bombardment history. Impact glass formed during asteroid and comet collisions has been preserved for billions of years due to the lack of weathering processes. This impact glass contains chemical signatures from the impacting objects, providing scientists with samples of the materials that were present in the inner solar system during its chaotic youth. Analysis of Mercury's impact glass has revealed evidence of water-bearing objects striking the planet throughout its history. Despite Mercury's current extreme conditions, the chemical signatures preserved in ancient impact glass suggest that water-rich comets regularly delivered volatile materials to the inner solar system. Some of this water may have been the source of the ice deposits now preserved in Mercury's polar regions, representing a direct connection between the planet's extreme present and its more volatile past. Mercury's surface features also record the ongoing evolution of the planet's internal structure. The global cliff systems, called lobate scarps, continue to grow as Mercury's interior slowly cools and contracts. Some of these cliffs show evidence of recent activity, with fresh scarps cutting across younger surface features. This ongoing geological activity demonstrates that Mercury remains a dynamic world despite its extreme environment. The extreme temperature cycles have created unique erosion processes that slowly modify Mercury's surface features. Thermal expansion and contraction cause rocks to develop stress fractures that gradually weaken surface structures. Over millions of years, this thermal weathering can significantly alter the appearance of surface features, creating erosion patterns that exist nowhere else in the solar system. Perhaps most remarkably, Mercury's extreme surface environment continues to reveal new surprises with each detailed observation. Recent high-resolution images have shown evidence of recent landslides and mass-wasting events, suggesting that the planet's extreme thermal environment drives ongoing geological activity. These discoveries challenge assumptions about Mercury being a geologically dead world and demonstrate that extreme conditions can drive planetary processes in unexpected ways. The study of Mercury's surface features provides crucial insights for understanding rocky exoplanets that orbit close to their host stars. Many of these distant worlds experience even more extreme conditions than Mercury, making the lessons learned from studying Mercury's geology essential for interpreting observations of similar planets around other stars. Mercury serves as our closest laboratory for understanding how rocky surfaces respond to extreme stellar radiation and temperature cycling. As we continue our journey through Mercury's extreme landscape, we'll explore how these surface features interact with the planet's tenuous atmosphere and magnetic environment to create a world where every component operates at the limits of planetary physics. Mercury's surface doesn't exist in isolation, but represents one part of an integrated system where extreme conditions create feedback loops that amplify and modify each other in ways that exist nowhere else in the known universe. Nowhere else in the known universe. The extreme surface features of Mercury exist within an envelope of gas so tenuous it barely qualifies as an atmosphere. Yet this gossamer thin layer of atoms and molecules plays a crucial role in the planet's extreme environment, creating phenomena that exist nowhere else in the solar system. Mercury's atmosphere is constantly being destroyed and recreated in an endless cycle driven by the planet's proximity to the Sun and its unique geological processes. To understand just how extraordinary Mercury's atmosphere truly is, consider that it contains less than 1/1,000,000,000th the amount of gas found in Earth's atmosphere. If you could somehow transport Mercury's entire atmospheric mass to Earth, it would create a layer barely thick enough to register on the most sensitive instruments. Yet within this almost non-existent envelope of gas, some of the most dynamic atmospheric processes in the solar system unfold on a daily basis. Mercury's atmosphere consists primarily of oxygen, sodium, hydrogen, helium, and potassium. But these elements don't exist in stable atmospheric layers as they do on other planets. Instead, they form what scientists call an exosphere, a region where individual atoms rarely collide with each other and instead follow ballistic trajectories like tiny spacecraft orbiting the planet. Each atom in Mercury's exosphere is essentially in its own independent orbit around the planet, creating an atmospheric environment unlike anything found elsewhere. The source of Mercury's atmospheric gases reveals the extreme processes that constantly reshape this world. Unlike Earth's atmosphere, which formed from volcanic outgassing and has been relatively stable for billions of years, Mercury's exosphere is continuously replenished through violent processes that tear atoms directly from the planet's surface. Solar wind particles slam into Mercury's crust with such energy that they literally knock atoms free from the rocky surface in a process called sputtering. Micrometeorites constantly bombard the planet, vaporizing tiny amounts of surface material with each impact. Perhaps most remarkably, the extreme temperature variations on Mercury's surface drive a process called thermal desorption, where atoms become so energetically excited by solar heating that they escape directly from the mineral structures that contain them. During Mercury's intense day, surface temperatures become so extreme that certain elements literally boil off the planet's surface, escaping into space in a continuous stream of vaporized rock. This atmospheric escape process occurs at rates that would strip away Earth's entire atmosphere in just a few million years. Mercury loses atmospheric material so rapidly that its entire exosphere is completely replaced every few months. The planet must continuously generate new atmospheric gases to maintain even its incredibly thin envelope, creating one of the most dynamic atmospheric systems in the solar system. The seasonal variations in Mercury's atmosphere reflect the planet's extreme orbital characteristics. As Mercury swings closer to the Sun during its elliptical orbit, The increased solar radiation intensifies all the atmospheric generation processes. Thermal desorption increases dramatically. Solar wind sputtering becomes more efficient, and the rate of micrometeorite impacts rises due to the increased gravitational focusing of debris toward the planet. During these periods of maximum atmospheric generation, Mercury's exosphere can become several times denser than during its more distant orbital phases. The composition of Mercury's atmosphere also varies dramatically with location and time. Sodium atoms, liberated from the planet's surface by impact processes and thermal desorption, create glowing clouds that can be observed from Earth using specialized telescopes. These sodium clouds extend far beyond Mercury's surface, forming comet-like tails that stream away from the planet under pressure from solar radiation. The sodium tail can extend for millions of miles behind Mercury, creating one of the most spectacular atmospheric phenomena in the solar system. Oxygen in Mercury's atmosphere comes primarily from the breakdown of water molecules delivered by comet impacts. When these water molecules are hit by solar ultraviolet radiation, they dissociate into hydrogen and oxygen atoms. The lightweight hydrogen escapes to space almost immediately, while the heavier oxygen atoms remain in the exosphere for longer periods before they too are lost to space. This process creates an ongoing cycle where water delivered by comets is continuously broken down and lost, requiring constant replenishment to maintain even trace amounts of oxygen in the atmosphere. The interaction between Mercury's weak magnetic field and its tenuous atmosphere creates electromagnetic phenomena that exist nowhere else in the solar system. Charged particles in the solar wind become trapped by Mercury's magnetic field lines and spiral down into the upper atmosphere, where they collide with atmospheric atoms to create aurora displays in X-ray wavelengths. These high-energy auroras are among the most intense electromagnetic phenomena in the inner solar system, releasing energy equivalent to millions of lightning strikes occurring simultaneously. Mercury's atmospheric dynamics are further complicated by the planet's unusual rotation and orbital characteristics. The 3-to-2 spin-orbit resonance means that different regions of the planet experience vastly different atmospheric conditions depending on their orientation relative to the Sun. Areas that face the Sun during Mercury's closest approach to the star experience atmospheric generation rates that are orders of magnitude higher than regions that remain in shadow. The extreme temperature gradients between Mercury's day and night sides drive atmospheric circulation patterns that operate on entirely different principles than weather systems on other planets. Instead of wind-driven circulation, Mercury's atmospheric flow is dominated by ballistic transport, where atoms heated on the day side gain enough energy to follow parabolic trajectories that carry them to the night side. This creates a slow but continuous atmospheric circulation that helps redistribute materials around the planet. Recent computer models of Mercury's atmospheric dynamics have revealed that the planet's exosphere exhibits complex seasonal and diurnal variations that reflect the intricate interplay between solar radiation, surface composition, and magnetic field interactions. During certain orbital configurations, the atmospheric density above Mercury's poles can be dramatically different from equatorial regions, creating atmospheric gradients that change on timescales of hours as the planet rotates. The study of Mercury's atmosphere has provided crucial insights into atmospheric escape processes that affect all terrestrial planets. The extreme conditions at Mercury represent an accelerated version of the atmospheric loss processes that operate more slowly on Mars and Venus. Understanding how Mercury's atmosphere behaves under such extreme conditions helps scientists model the long-term evolution of atmospheres throughout the solar system and around other stars. Mercury's atmospheric composition also preserves chemical signatures from the planet's geological processes. The ratios of different elements in the exosphere reflect the mineral composition of surface materials and the efficiency of various atmospheric generation mechanisms. Spectroscopic analysis of Mercury's sodium clouds, for example, has revealed details about the planet's crustal composition that complement direct surface observations from orbiting spacecraft. The interaction between Mercury's atmosphere and its surface creates feedback loops that influence both atmospheric and geological processes. Atoms that escape from the day side and condense on the night side can become incorporated into surface minerals, only to be released again during subsequent heating cycles. This atmospheric geological cycling helps redistribute volatile elements across Mercury's surface and contributes to the chemical gradients observed in different regions. Perhaps most remarkably, Mercury's tenuous atmosphere plays a role in the planet's thermal budget. While too thin to significantly moderate temperature variations, the exosphere does absorb and re-emit a small fraction of solar radiation, creating subtle but measurable effects on surface temperatures. These atmospheric heating effects are most pronounced during Mercury's closest approaches to the Sun, when atmospheric density reaches its maximum values. The extreme nature of Mercury's atmospheric environment has made it a target for studying fundamental atmospheric physics under conditions that cannot be replicated in laboratory settings. The planet serves as a natural experiment in atmospheric dynamics, where scientists can observe how gases behave under the influence of intense radiation, extreme temperature variations, and minimal gravitational retention. Mercury's atmospheric escape processes also provide insights into the early evolution of terrestrial planet atmospheres. During the solar system's youth, when the Sun was more active and solar wind intensities were higher, all the inner planets may have experienced atmospheric loss rates similar to what Mercury endures today. Understanding Mercury's current atmospheric dynamics helps scientists reconstruct the atmospheric history of Earth, Venus, and Mars during their formative periods. The ongoing loss of Mercury's atmosphere to space represents one of the most extreme examples of atmospheric evolution in the solar system. Over geological timescales, Mercury has likely lost atmospheric masses equivalent to entire planetary atmospheres multiple times over. This continuous atmospheric renewal and loss creates a dynamic equilibrium where the planet maintains a tenuous envelope of gas, despite the constant forces working to strip it away. As we prepare to explore Mercury's most mysterious features, including its unexpected polar ice deposits and actively forming surface features, remember that even the planet's barely detectable atmosphere plays a crucial role in its extreme environment. The thin envelope of atoms surrounding Mercury participates in chemical cycles, electromagnetic interactions, and thermal processes that connect the planet's surface, interior, and space environment in ways that create one of the most complex and dynamic planetary systems in our solar system. The atmospheric story of Mercury demonstrates how extreme conditions can drive planetary processes in unexpected directions. Rather than simply being a passive remnant of planetary formation, Mercury's atmosphere represents an active component of the planet's environmental system, continuously renewed by the same extreme forces that make this world one of the most challenging places in the solar system. This dynamic atmospheric system serves as a bridge between Mercury's solid surface and the harsh environment of interplanetary space, mediating interactions that help define the planet's unique character among the worlds of our solar system. The interplay between Mercury's tenuous atmosphere and its extreme surface conditions creates opportunities for atmospheric phenomena that exist nowhere else. Dust devils driven by extreme temperature gradients can loft surface particles high into the exosphere, creating temporary clouds of material that slowly settle back to the surface over periods of days or weeks. These dust clouds can temporarily alter the optical properties of Mercury's atmosphere, creating subtle but detectable changes in how the planet reflects sunlight. The atmospheric chemistry of Mercury operates under conditions so extreme that they push chemical reaction rates to their theoretical limits. The intense solar ultraviolet radiation creates a highly reactive chemical environment where even normally stable compounds can be broken down and reformed on rapid timescales. This creates an atmospheric laboratory where scientists can study chemical processes under radiation conditions that far exceed anything found in Earth's atmosphere. Mercury's atmospheric escape mechanisms also create unique isotopic signatures that preserve records of the planet's thermal history. As lighter isotopes escape to space more readily than heavier ones, the remaining atmospheric gases become progressively enriched in heavy isotopes over time. Analysis of these isotopic ratios provides insights into how long Mercury has been losing its atmosphere and how the escape rates have changed throughout the planet's history. The magnetic field interactions with Mercury's atmosphere create particle acceleration mechanisms that exist nowhere else in the inner solar system. Atmospheric atoms become ionized by solar radiation and then accelerated by electromagnetic fields to velocities approaching significant fractions of the speed of light. These high-energy particles create radiation environments around Mercury that are among the most intense found anywhere in the solar system outside the immediate vicinity of the Sun itself. As Mercury continues its eternal dance around the Sun, its atmosphere remains one of the most dynamic and ephemeral features of this extreme world. The constant destruction and renewal of atmospheric gases creates a planetary environment that exists in a perpetual state of change, where the very air around the planet is continuously being rewritten by the forces of stellar radiation, impact bombardment, and thermal processing. The atmospheric story of Mercury connects directly to the planet's most surprising discovery: the vast deposits of water ice hidden in its polar regions. These ice deposits exist in an environment where the atmosphere above them is so thin it offers no protection from space, yet they have persisted for potentially billions of years in one of the most extreme thermal environments in the solar system. Understanding how Mercury's atmosphere interacts with these ice deposits reveals one of the most remarkable examples of environmental contrast anywhere in the known universe. The study of Mercury's atmospheric dynamics continues to yield new insights into how planetary atmospheres behave under extreme conditions. Each observation adds another piece to the puzzle of how this remarkable world maintains its tenuous envelope of gas while enduring some of the most punishing conditions imaginable. Mercury's atmosphere may be barely detectable, but its influence on the planet's extreme environment is both profound and essential. for understanding how this world operates at the very limits of planetary physics. Limits of planetary physics. In Mercury's polar regions lies perhaps the most stunning contradiction in our solar system. Here, in permanently shadowed craters where temperatures plunge to -370 degrees Fahrenheit, vast deposits of water ice have accumulated over billions of years. This discovery initially seemed impossible to most planetary scientists. How could billions of tons of ice exist on a world where midday temperatures regularly exceed 800 degrees Fahrenheit, hot enough to melt lead? The answer reveals one of nature's most extraordinary examples of environmental extremes coexisting within meters of each other. Mercury's rotational axis tilts less than 1 degree relative to its orbital plane, meaning the Sun never rises more than a few degrees above the horizon at the planet's poles. Deep impact craters in these regions create permanent shadows that have remained untouched by direct sunlight for geological ages, possibly since the craters formed billions of years ago. Within these eternal shadows, temperatures remain so frigid that water ice becomes as stable as granite. The thermal environment in these polar cold traps is more extreme than the surface of Pluto, creating conditions where not only water ice, but also frozen carbon dioxide, sulfur compounds, and other volatiles can accumulate and persist for cosmic timescales. These deposits represent some of the most ancient ice in the solar system, potentially preserving samples of the water that was present during the solar system's violent youth. The detection of these ice deposits required some of the most sophisticated remote sensing techniques ever developed. Earth-based radar observations first hinted at their existence when radio waves bounced off Mercury's poles showed signatures consistent with nearly pure water ice. The signals were so clear and strong that they indicated deposits several meters thick, covering areas equivalent to large cities on Earth. When NASA's Messenger spacecraft arrived at Mercury, it carried instruments specifically designed to confirm and map these mysterious ice deposits. The neutron spectrometer detected the characteristic signature of hydrogen atoms locked within water molecules, providing definitive proof that the radar observations were correct. Thermal modeling confirmed that the permanently shadowed regions maintain temperatures cold enough to preserve ice for billions of years. The total amount of ice in Mercury's polar regions is staggering. Conservative estimates suggest at least 100 billion tons of water ice, with some models indicating the deposits could contain 10 times that amount. To put this in perspective, Mercury's polar ice deposits contain more water than some of the smaller moons in the outer solar system. This represents one of the largest known reservoirs of water ice in the inner solar system outside of Earth itself. The origin of this ice adds another layer of mystery to Mercury's extreme story. The most likely source is cometary impacts that occurred throughout Mercury's history. When water-rich comets struck Mercury, most of the water would have vaporized instantly upon impact with the scorching surface. However, some fraction of the impact debris could have been ejected at high angles, allowing it to rain down into the permanently shadowed polar regions where it could freeze and accumulate. Computer simulations of this process reveal that it would take millions of comet impacts over billions of years to build up the observed ice deposits. Each impact would contribute only a tiny fraction of the total ice mass, but the cumulative effect over geological time could account for the vast deposits we see today. This process connects Mercury's ice deposits directly to the bombardment history of the entire inner solar system. making them a record of water delivery during the solar system's chaotic early epochs. The preservation of these ice deposits requires a delicate balance of extreme conditions. The permanently shadowed regions must remain cold enough to prevent sublimation, while the surrounding areas experience some of the hottest surface temperatures in the solar system. The boundary between ice and bare rock can occur across distances of just a few meters, creating temperature gradients of over 1,000 degrees across spaces smaller than a city block. Recent high-resolution mapping has revealed that the ice deposits have complex internal structures reflecting millions of years of accumulation and modification. Some areas show evidence of layering, suggesting that the ice was deposited during discrete episodes separated by long periods of minimal accumulation. Other regions display signs of sublimation and redeposition, where ice at the edges of deposits slowly vaporizes and moves to even colder areas deeper within the shadows. The ice deposits also show evidence of contamination by other materials delivered during the same impact events that brought the water. Spectroscopic analysis suggests that the ice contains significant amounts of organic compounds, possibly including complex carbon-based molecules that formed in the outer solar system and were delivered to Mercury by comets. These organic materials could provide insights into the chemical processes that occurred during the solar system's formation. The thermal properties of Mercury's polar ice deposits reveal additional extreme characteristics. The ice exists in a state of permanent winter that is more severe than anything found on Earth, even in Antarctica. The combination of extremely low temperatures and the vacuum environment of space creates ice with properties that differ significantly from terrestrial ice. The material becomes harder than many rocks, yet it can also sublime directly to vapor without melting when exposed to even minimal heating. The interaction between these ice deposits and Mercury's tenuous atmosphere creates unique chemical processes. When solar radiation occasionally penetrates into the shadowed regions, or when micrometeorite impacts disturb the ice, small amounts of water vapor are released into the exosphere. This water vapor quickly dissociates under the intense solar ultraviolet radiation, contributing hydrogen and oxygen to Mercury's atmospheric inventory. The polar ice deposits also influence Mercury's thermal environment in subtle but measurable ways. The high reflectivity of the ice surfaces helps to maintain the extreme cold within the permanently shadowed regions by reflecting away any scattered sunlight that might penetrate the shadows. This creates a feedback loop where the presence of ice helps to maintain the conditions necessary for its own preservation. Recent discoveries have revealed that the ice deposits extend much deeper into Mercury's subsurface than originally thought. Radar penetration studies suggest that in some regions, the ice may extend several tens of meters below the surface, indicating that the accumulation process has been operating for extremely long periods. These subsurface ice layers are even better protected from sublimation than the surface deposits, creating reservoirs that could persist even if surface conditions change. The boundaries between ice and rock in Mercury's polar regions create unique geological environments. The extreme temperature contrasts drive thermal expansion and contraction cycles that fracture both ice and rock, creating complex mixtures of frozen and solid materials. These boundary zones represent some of the most geologically active regions on Mercury, where ongoing freeze-thaw cycles continue to modify the landscape. The discovery of organic compounds within Mercury's ice deposits has profound implications for astrobiology and our understanding of how complex molecules behave under extreme conditions. The organic materials have been preserved in a deep freeze for potentially billions of years, creating a natural laboratory for studying how carbon-based compounds evolve in space environments. Some of these molecules might be similar to the organic materials that were present on early Earth, providing insights into the chemical ingredients that were available for the origin of life. The polar ice deposits also serve as a record of the solar system's impact history. Each layer of ice potentially preserves chemical signatures from the comet that delivered it, creating a stratigraphic record of the types of objects that were striking Mercury throughout its history. Analysis of different layers could reveal how the composition of comets changed over time as the solar system evolved. The extreme environmental contrasts in Mercury's polar regions create opportunities for studying phase transitions under conditions that cannot be replicated in terrestrial laboratories. The boundaries between different types of ice, between ice and rock, and between frozen and gaseous phases occur under pressure and temperature conditions that push the limits of our understanding of matter behavior. Perhaps most remarkably, the polar ice deposits demonstrate that even the most extreme planetary environments can preserve materials over cosmic timescales. The fact that water ice can survive for billions of years just meters away from some of the hottest surface temperatures in the solar system reveals the power of environmental niches to protect materials from otherwise destructive conditions. The ongoing study of Mercury's polar ice deposits continues to yield surprises about both the planet's history and the behavior of materials under extreme conditions. Each new observation adds detail to our understanding of how these remarkable deposits formed, how they've survived for so long, and what they can tell us about the early solar system's evolution. The polar ice story connects directly to Mercury's most mysterious surface features, the actively forming hollows that appear across the planet's landscape. Both phenomena demonstrate that Mercury remains a dynamic world where geological and chemical processes continue to operate under conditions so extreme they exist nowhere else in the known universe. The ice deposits and the mysterious hollows represent different expressions of how Mercury's extreme environment drives planetary processes that challenge our understanding of what's possible when matter encounters the limits of physical endurance. The juxtaposition of billion-year-old ice deposits and actively forming geological features makes Mercury a world where ancient preservation and ongoing change coexist in ways that defy simple explanation. This remarkable planet continues to reveal new aspects of its extreme nature with each detailed observation, demonstrating that the boundaries of planetary science extend far beyond what we once thought possible. The story of Mercury's polar ice deposits serves as a bridge to understanding the planet's most enigmatic features, the bright hollows that dot its surface like cosmic artwork. These features represent active geology occurring under the most extreme conditions imaginable, proving that Mercury's story of extremes continues to unfold in real time across its ancient yet dynamic landscape. Among all the mysterious features scattered across Mercury's scarred landscape, none are more perplexing than the bright hollows that appear like cosmic punctuation marks against the planet's ancient terrain. These enigmatic depressions, first discovered during Messenger's detailed reconnaissance of the planet, represent one of the most active geological processes currently operating on Mercury. Unlike the billion-year-old ice deposits hidden in polar shadows, these hollows appear to be forming right now, carved into the planet's surface by forces so unusual that scientists are still debating their exact nature. Picture standing at the rim of one of these mysterious features. Below you stretches a depression that might span several kilometers across, its floor gleaming with an almost mirror-like brightness that stands out dramatically against Mercury's typically dark terrain. The walls of the hollow drop away in irregular patterns, creating a landscape that looks almost organic, as if something has been systematically eating away at the rocky surface from within. The brightness of these features is so intense that they can be detected from orbit, using instruments designed to measure the subtle variations in how different materials reflect sunlight. The distribution of hollows across Mercury's surface tells a fascinating story about the planet's extreme environment. These features cluster preferentially in regions that experience the most intense solar heating, particularly areas that face the sun during Mercury's closest approaches to our star. They tend to form within impact craters, especially on crater walls and central peaks, where certain types of rock are exposed. Some hollows appear in isolation, like solitary scars on the landscape, while others form complex networks of interconnected depressions that can extend for dozens of kilometers. What makes these hollows truly extraordinary is their apparent youth. In the context of a planet that's 4.5 billion years old, these features appear to have formed within the last few million years, perhaps even more recently. Some show evidence of ongoing formation, with fresh, bright material appearing at their edges and floors that suggest active excavation processes. The discovery of such young geological features on a world that was thought to be essentially geologically dead represents one of the biggest surprises in planetary science. The formation mechanism for Mercury's hollows involves processes so extreme they exist nowhere else in the solar system. The leading scientific theory suggests that certain sulfide minerals in Mercury's crust become unstable under the planet's intense thermal and radiation environment. When these minerals are exposed to the combination of extreme solar heating and high-energy particle bombardment, they begin to break down at the molecular level, literally vaporizing away and leaving behind the characteristic hollow depressions. This process, known as thermal sublimation, enhanced by space weathering, operates like a slow-motion explosion occurring over geological timescales. The sulfide minerals that formed billions of years ago when Mercury's crust solidified contain volatile elements that become increasingly unstable as they're exposed to the planet's extreme surface conditions. Solar ultraviolet radiation and high-energy particles from the solar wind provide the energy needed to break the chemical bonds holding these minerals together, causing them to decompose and release gases that escape directly to space. The brightness of the hollow floors provides crucial clues about this formation process. As the unstable minerals sublimate away, they leave behind residual materials with different optical properties than the original rock. These residual materials tend to be highly reflective, creating the characteristic bright appearance that makes hollows so distinctive. Spectroscopic analysis suggests that the bright material might consist of minerals that are more resistant to thermal breakdown, concentrated as the less stable components are selectively removed. The ongoing nature of hollow formation has been confirmed through comparison of images taken at different times during MESSENGER's mission. Some hollows showed measurable expansion over periods of just a few years. proving that these features are actively growing rather than simply being ancient scars slowly revealed by erosion. The rate of hollow growth appears to correlate with Mercury's orbital position, with faster expansion occurring during periods when the planet receives maximum solar radiation. The extreme conditions required for hollow formation help explain why these features exist only on Mercury. The process requires a unique combination of intense solar radiation, high-energy particle bombardment, extreme temperature cycling, and specific mineral compositions that occur together only on the innermost planet. Even Venus, despite its proximity to the Sun, lacks the necessary combination of factors because its thick atmosphere shields the surface from the direct particle bombardment that appears essential for hollow formation. The chemical composition of the materials being removed during hollow formation provides insights into Mercury's crustal makeup. The sulfide minerals that appear most susceptible to thermal breakdown contain elements like sulfur, sodium, and potassium that become volatile under Mercury's extreme conditions. As these elements are liberated from the crystal structures, they contribute to Mercury's tenuous atmosphere before escaping to space, creating a direct connection between surface geology and atmospheric chemistry. Recent computer models of the hollow formation process reveal that the thermal and radiation environment within these depressions becomes increasingly extreme as they grow larger. The geometry of the hollows can focus and concentrate solar radiation, creating localized hotspots where temperatures exceed even Mercury's already extreme surface conditions. These enhanced thermal environments accelerate the sublimation process, creating a feedback loop where hollow formation becomes self-sustaining once it begins. As the distribution of different types of hollows across Mercury's surface reflects variations in crustal composition and thermal history. Simple hollows, consisting of single depressions with relatively smooth floors, tend to form in areas with uniform rock composition. Complex hollow systems, featuring multiple interconnected depressions and irregular boundaries, develop where the underlying geology includes multiple rock types with different susceptibilities to thermal breakdown. Some of the most spectacular hollow complexes occur within Mercury's largest impact craters, where the ancient collisions excavated deep into the planet's crust and exposed materials that had been protected from surface conditions for billions of years. When these buried materials are suddenly exposed to Mercury's extreme surface environment, they can undergo rapid thermal decomposition that creates extensive hollow systems spanning tens of kilometers. The temporal evolution of hollow formation reveals additional insights into Mercury's extreme environment. Early in their development, hollows tend to be small and circular, reflecting the initial exposure of unstable minerals to surface conditions. As the sublimation process continues, the hollows grow both outward and downward, eventually developing the irregular shapes and complex internal structures observed in mature examples. The interaction between hollow formation and Mercury's extreme temperature cycles creates unique microenvironments within these depressions. The walls and floors of hollows experience different thermal histories than the surrounding terrain, leading to variations in the rates and patterns of mineral breakdown. Some areas within hollows show evidence of multiple episodes of formation and modification, suggesting that the process operates in cycles related to Mercury's orbital variations. The study of hollow formation has revealed that Mercury's surface is far more chemically active than previously imagined. Rather than being a geologically dead world shaped entirely by ancient processes, Mercury hosts ongoing chemical reactions driven by its extreme environment. These reactions operate on timescales that are rapid by geological standards, demonstrating that extreme conditions can accelerate normally slow geological processes by factors of millions or billions. The hollows also provide natural laboratories for studying how materials behave under radiation and thermal conditions that far exceed anything found on Earth. The mineral transformations occurring within these features involve processes that push chemical bonds to their breaking points, creating opportunities to study matter under extreme stress. Understanding these processes has applications beyond planetary science, potentially informing materials research and space technology development. The discovery of actively forming hollows has implications for understanding the long-term evolution of Mercury's surface and interior. The ongoing loss of material through hollow formation represents a form of planetary erosion that operates from the inside out, gradually removing certain components of Mercury's crust and redistributing them to space. Over millions of years, this process could significantly alter the chemical composition of Mercury's surface layers. The hollow formation process also demonstrates how Mercury's extreme environment creates positive feedback loops that amplify geological activity. As hollows expose fresh material to surface conditions, they create new sites where thermal breakdown can occur. The process becomes self-perpetuating, with each new exposure leading to additional material loss and further hollow development. Perhaps most remarkably, the study of Mercury's hollows has revealed that extreme planetary environments can drive geological processes that operate according to entirely different principles than those familiar from Earth. While terrestrial geology is dominated by processes involving liquid water, plate tectonics, and atmospheric weathering, Mercury's geology operates through mechanisms involving direct solid-to-gas transitions, particle bombardment, and thermal cycling that create landscapes unlike anything found elsewhere. The ongoing formation of hollows makes Mercury one of the most geologically active worlds in the inner solar system, despite its reputation as a dead planet. The extreme conditions that initially seemed to preclude geological activity actually drive unique processes that reshape the planetary surface in ways that exist nowhere else in the known universe. These features represent the intersection of planetary science, chemistry, and physics, operating under conditions that push the boundaries of what's possible when matter encounters the most extreme environments nature can create. The hollow story connects to Mercury's broader narrative of extremes, demonstrating how this remarkable world continues to surprise scientists with evidence of active processes occurring under conditions that challenge our understanding of planetary behavior. Each new observation of these mysterious features adds another piece to the puzzle of how extreme environments can drive planetary evolution in directions that seem to defy conventional geological wisdom. As we continue our exploration of Mercury's extraordinary nature, the hollows serve as a reminder that this planet represents far more than just a hot, radiation-blasted rock. Mercury emerges as a world where extreme conditions create opportunities for geological processes that exist nowhere else, making it a unique laboratory for studying how planetary systems operate when pushed to their absolute limits. The formation and evolution of Mercury's hollows illustrate the planet's role as a cosmic testing ground, where the fundamental forces of the universe interact under the most challenging conditions imaginable. Understanding these processes provides crucial insights for interpreting similar phenomena that might exist on the thousands of rocky exoplanets we've discovered orbiting other stars, many of which experience even more extreme conditions than Mercury's already punishing environment. The story of Mercury's actively forming hollows represents just one chapter in the ongoing saga of discovery that makes this extreme world one of the most scientifically valuable targets in our solar system. Every observation reveals new aspects of how planetary processes operate under conditions that stretch the boundaries of physics, chemistry, and geology in ways that continue to astonish researchers and reshape our understanding of what's possible in planetary science. These bright scars scattered across Mercury's ancient landscape serve as windows into active planetary processes occurring under the most extreme conditions in our solar system. They remind us that even in environments that seem utterly hostile to change, nature finds ways to continue sculpting and reshaping planetary surfaces through mechanisms that exist nowhere else in the known universe. The hollows stand as testament to Mercury's status as the most extreme planet in our solar system, a world where the impossible becomes routine and the boundaries of planetary science are constantly being rewritten by forces that push matter and energy to their absolute limits. Energy to their absolute limits. The story of Mercury's extreme nature extends far beyond its surface features and atmospheric phenomena. Hidden within the planet's orbital mechanics lies one of the most elegant confirmations of our understanding of space and time itself. Mercury's journey around the Sun follows a path that deviates slightly from what classical physics predicts, and this tiny deviation helped prove one of the most revolutionary theories in the history of science. When astronomers in the 19th century began making precise measurements of Mercury's orbit, they discovered something puzzling. The planet's elliptical path around the Sun wasn't quite where Newton's laws of gravity said it should be. Mercury's orbit exhibits what scientists call precession, where the entire elliptical path slowly rotates around the Sun over time. While Newton's gravitational theory predicted some precession due to the gravitational influence of other planets, Mercury's actual precession exceeded these predictions by 43 arc-seconds per century. This might sound like an insignificant discrepancy, but in the precise world of celestial mechanics, such deviations demand explanation. For decades, astronomers searched for the source of this extra precession. Some proposed the existence of an undiscovered planet orbiting closer to the Sun than Mercury, which they named Vulcan. Others suggested that the Sun might be slightly flattened, creating gravitational effects that could account for the anomaly. The true explanation came from Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity itself. Einstein showed that massive objects don't just attract other objects through some mysterious force acting across empty space. Instead, they actually curve the fabric of space and time, and objects follow the straightest possible paths through this curved space-time. What we experience as gravity is really the result of moving through curved space-time geometry. Mercury's extreme proximity to the Sun places it deep within the curved space-time created by our star's enormous mass. The planet experiences the curvature of space-time more intensely than any other world in our solar system, making it the perfect natural laboratory for testing Einstein's theory. The extra precession that puzzled 19th century astronomers matches exactly what general relativity predicts for a planet orbiting so close to such a massive star. This confirmation of Einstein's theory using Mercury's orbit represents one of the most elegant examples of how extreme environments can serve as testing grounds for fundamental physics. Mercury's position in the intense gravitational field near the Sun creates conditions where the effects of space-time curvature become measurable with 19th century instruments. Without Mercury's extreme orbital characteristics, this crucial test of general relativity might have remained impossible for decades longer. The gravitational environment that Mercury experiences involves forces so intense they literally reshape the flow of time itself. According to general relativity, time runs slightly slower in stronger gravitational fields, and Mercury sits deep enough in the Sun's gravitational well that this effect becomes measurable. A clock on Mercury's surface would run approximately 8 microseconds per year, slower than an identical clock floating in empty space, far from any gravitational influence. This time dilation effect, while tiny by everyday standards, accumulates over millions of years to create measurable changes in Mercury's orbital timing. The planet's extreme gravitational environment makes it a natural laboratory for studying how gravity affects the passage of time, providing insights into one of the most profound aspects of Einstein's theory. Mercury's orbital characteristics also reveal how extreme gravitational environments can affect the behavior of light itself. Photons traveling past the Sun experience gravitational deflection, with their paths bent by the curvature of space-time. Light grazing the Sun's surface is deflected by approximately 1 3/4 arcseconds, an effect that was first measured during solar eclipses and provided another crucial confirmation of general relativity. The intense gravitational field near Mercury creates additional relativistic effects that don't exist elsewhere in the solar system. The planet's motion through curved spacetime generates frame-dragging effects, where the rotation of the Sun actually drags spacetime around with it, creating additional perturbations in Mercury's orbit. These effects are incredibly small, but they represent measurable consequences of general relativity operating under the extreme conditions found in Mercury's neighborhood. The study of Mercury's orbital dynamics has also revealed how extreme gravitational environments affect the propagation of gravitational waves themselves. When Mercury accelerates in its elliptical orbit, it creates ripples in space-time that propagate outward at the speed of light. While these gravitational waves are far too weak to detect with current technology, their theoretical existence demonstrates how Mercury's extreme orbital characteristics connect it to some of the most exotic phenomena in modern physics. The thermal effects of Mercury's extreme orbital environment create additional complexities that push the boundaries of orbital mechanics. The intense solar heating causes the planet's solid surface to expand and contract, slightly altering its shape and therefore its gravitational field. These thermal deformations create tiny perturbations in Mercury's orbit that accumulate over time, adding another layer of complexity to the planet's already intricate orbital behavior. Mercury's eccentric orbit also subjects the planet to tidal forces that vary dramatically throughout its journey around the Sun. At perihelion, when Mercury approaches within 29 million miles of the Sun, tidal forces become so intense that they deform the planet's solid surface by several meters. These tidal bulges create additional gravitational effects that influence the planet's orbital evolution over cosmic timescales. The extreme radiation pressure that Mercury experiences during its close approaches to the Sun creates yet another exotic orbital effect. Solar radiation carries momentum, and when it strikes Mercury's surface, it exerts a tiny but measurable force that gradually alters the planet's orbit. This radiation pressure effect, known as the Yarkovsky effect, becomes significant only for objects with extreme thermal characteristics like Mercury. The interaction between Mercury's orbital dynamics and its magnetic field creates electromagnetic effects that exist nowhere else in the solar system. As the planet moves through the Sun's magnetic field, it generates electrical currents within its conducting core. These currents create additional magnetic fields that interact with the solar wind, producing complex electromagnetic phenomena that influence both Mercury's magnetic environment and its orbital behavior. Recent precision measurements of Mercury's orbit have revealed additional relativistic effects that were too small to detect with earlier technology. The planet's motion through space-time generates what physicists call geodetic precession, a rotation of the planet's spin axis caused by its motion through curved space-time. This effect demonstrates how Mercury's extreme gravitational environment affects not just its orbital motion, but also its rotational behavior. The extreme nature of Mercury's orbital environment has made it a crucial testing ground for alternative theories of gravity. Scientists have used precision measurements of Mercury's orbit to test modifications to general relativity that might explain dark matter and dark energy without invoking exotic forms of matter and energy. The planet's sensitivity to gravitational effects makes it one of the most valuable laboratories for fundamental physics research in the entire solar system. Mercury's orbital characteristics also provide insights into the long-term stability of planetary systems. The planet's extreme orbital environment subjects it to perturbations that could potentially destabilize its orbit over cosmic timescales. Computer simulations suggest that Mercury's orbit will remain stable for billions of years, but the planet's extreme characteristics make it more susceptible to orbital evolution than other terrestrial planets. The study of Mercury's orbital dynamics has revealed how extreme environments can amplify normally insignificant physical effects to measurable levels. The planet serves as a cosmic amplifier, where the intense gravitational and thermal conditions magnify relativistic and electromagnetic effects that would be undetectable in more moderate environments. Perhaps most remarkably, Mercury's extreme orbital characteristics have provided some of the most precise confirmations of our understanding of fundamental physics. The planet's motion through space-time matches theoretical predictions with extraordinary accuracy, demonstrating that our theories remain valid even under the most extreme conditions found in our solar system. The ongoing study of Mercury's orbital behavior continues to yield new insights into both planetary dynamics and fundamental physics. As our measurement techniques become more precise, Mercury's extreme environment reveals ever more subtle effects that test our understanding of gravity, electromagnetism, and the nature of space-time itself. The orbital story of Mercury connects directly to its role as a natural laboratory for studying how planetary systems evolve under extreme conditions. The planet's proximity to the Sun creates an environment where multiple physical processes operate simultaneously at their theoretical limits, providing opportunities to study complex interactions between gravitational, thermal, and electromagnetic forces. Mercury's extreme orbital characteristics also have implications for understanding the thousands of exoplanets we've discovered orbiting other stars. Many of these distant worlds orbit much closer to their host stars than Mercury does to the Sun, experiencing even more intense gravitational and thermal effects. Understanding how Mercury behaves under extreme conditions provides crucial insights for modeling the evolution and stability of these exotic planetary systems. The precision with which Mercury's orbit matches theoretical predictions serves as a powerful validation of our understanding of how the universe operates at its most fundamental level. In an age when new discoveries in physics often require billion-dollar particle accelerators or space-based gravitational wave detectors, Mercury provides a natural laboratory where some of the most profound questions in physics can be studied using the same telescopes that astronomers have used for centuries. The extreme nature of Mercury's orbital environment ensures that this remarkable planet will continue serving as a testing ground for fundamental physics for generations to come. As our theories become more sophisticated and our measurements more precise, Mercury's unique position in the intense gravitational field near the Sun will undoubtedly reveal new phenomena that challenge and refine our understanding of how the universe works. The orbital dynamics of Mercury represent just one more aspect of this planet's claim to being the most extreme world in our solar system. From its scorching surface, temperatures to its mysterious magnetic field, from its tenuous atmosphere to its hidden ice deposits, every characteristic of Mercury pushes the boundaries of what we consider possible in planetary science. The planet's orbital behavior adds another dimension to this extremeness, demonstrating how proximity to a massive star can create conditions where the fundamental laws of physics reveal themselves in ways that exist nowhere else in our cosmic neighborhood. As Mercury continues its eternal dance around the Sun, traveling its precisely measured path through curved space-time, it carries with it the distinction of being not just the most extreme planet in our solar system, but also one of the most scientifically valuable. Every orbit provides new opportunities to test our understanding of gravity, time, and space under conditions that push these phenomena to their observable limits. The story of Mercury's orbital extremes serves as a bridge between the planet's physical characteristics and its broader significance for science and human understanding. This small, seemingly simple world harbors complexities that connect planetary science to the deepest questions about the nature of reality itself, making it a cosmic treasure trove of scientific discovery that continues to surprise and enlighten researchers with each new observation. In the grand symphony of planetary motions that fills our solar system, Mercury plays a unique role as the world that dances closest to our star, experiencing gravitational and thermal extremes that reveal the universe's most fundamental secrets. Its orbital precision serves as a cosmic metronome, keeping time with mathematical perfection while simultaneously demonstrating how extreme conditions can serve as windows into the deepest truths about the cosmos we inhabit. The extreme orbital dynamics of Mercury create cascading effects that ripple through every aspect of this remarkable world's existence. As the planet completes its 88-day journey around the Sun, the varying intensity of solar radiation doesn't just heat the surface differently, it drives atmospheric processes, influences magnetic field interactions, and creates thermal stress patterns that actively reshape the planet's geology in real time. During Mercury's closest approach to the Sun at perihelion, the planet receives nearly twice as much solar energy per square meter as it does at its farthest point. This dramatic variation in energy input creates seasonal effects that dwarf anything experienced on Earth. Imagine if our planet's summer delivered twice as much solar energy as winter, not just through longer days or higher sun angles, but through a fundamental change in the intensity of stellar radiation itself. These extreme seasonal variations drive atmospheric dynamics that exist nowhere else in the solar system. Mercury's tenuous exosphere expands and contracts dramatically as the planet swings closer to and farther from the Sun. During perihelion passages, the increased solar heating drives atmospheric escape rates to their maximum values, while the enhanced solar wind pressure strips away atmospheric particles at accelerated rates. The result is an atmosphere that breathes with Mercury's orbital rhythm, expanding during close solar approaches and contracting during more distant phases. The thermal cycling driven by these orbital variations penetrates deep into Mercury's interior, influencing processes that occur hundreds of kilometers below the surface. The varying tidal forces as Mercury's distance from the Sun changes create pressure waves that propagate through the planet's core, potentially contributing to the convection patterns that sustain its magnetic field. These deep thermal effects represent one of the most extreme examples of how orbital mechanics can directly influence planetary interior dynamics. The electromagnetic environment around Mercury also pulses with the planet's orbital rhythm. During close solar approaches, the intensified solar wind compresses Mercury's magnetosphere, creating radiation environments that fluctuate dramatically throughout each orbit. Charged particles trapped in Mercury's magnetic field become accelerated to higher energies during these compression events, creating aurora displays that intensify and fade with mathematical precision tied to the planet's orbital position. Mercury's extreme orbital characteristics have also shaped its rotational behavior in ways that amplify the planet's already extraordinary thermal environment. The 3-to-2 spin-orbit resonance means that the same regions don't always face the Sun during closest approach. Instead, different parts of Mercury experience maximum solar heating during different orbital cycles, creating complex thermal patterns that vary on timescales of multiple Mercury years. This rotational complexity produces what scientists call thermal seasons that operate independently of Mercury's orbital seasons. Some regions experience their hottest conditions when Mercury is near aphelion, while others reach maximum temperatures during perihelion passages. The result is a planet where thermal extremes shift across the surface in patterns so complex they require sophisticated computer models to predict and understand. The interaction between Mercury's extreme orbital and rotational characteristics creates surface temperature patterns that challenge our understanding of planetary thermal physics. Some locations experience temperature variations that span nearly 1500 degrees Fahrenheit throughout a single Mercury day, while others maintain relatively stable temperatures due to their orientation relative to the Sun's path across Mercury's sky. These thermal complexities drive geological processes that operate according to entirely different principles than those familiar from other terrestrial planets. The constant thermal expansion and contraction creates stress fields within Mercury's crust that shift and evolve as different regions experience their maximum and minimum heating cycles. Over millions of years, these shifting stress patterns have created fracture networks that extend deep into the planet's interior. The extreme nature of Mercury's orbital environment has also influenced its atmospheric chemistry in ways that create unique molecular processes. The varying intensity of solar ultraviolet radiation throughout Mercury's orbit drives photochemical reactions at rates that fluctuate dramatically with orbital position. During perihelion passages, atmospheric molecules experience radiation doses intense enough to break apart even normally stable compounds, while quieter periods allow different chemical species to form and persist. Recent computer simulations have revealed that Mercury's orbital extremes create resonances between the planet's thermal cycles and its atmospheric dynamics. Certain atmospheric oscillations become synchronized with Mercury's orbital period, creating standing wave patterns in the exosphere that persist for multiple orbital cycles. These atmospheric resonances represent one of the most exotic examples of orbital atmospheric coupling found anywhere in the solar system. The gravitational environment that Mercury experiences during its close solar approaches creates tidal effects so intense they influence the planet's magnetic field in real time. As Mercury swings through perihelion, the changing tidal forces deform the planet's shape slightly, altering the circulation patterns within its liquid core. These changes in core dynamics create measurable variations in magnetic field strength that correlate directly with Mercury's orbital position. The extreme radiation environment that Mercury encounters during its closest approaches to the Sun subjects the planet to particle bombardment rates that fluctuate by orders of magnitude throughout each orbit. During perihelion passages, high-energy particles from solar flares and coronal mass ejections strike Mercury's surface with intensities that would be lethal to any known form of life. These radiation storms occur with frequencies and intensities that make Mercury's radiation environment one of the most variable and extreme in the solar system. The thermal processing that occurs during Mercury's most intense solar heating periods drives chemical reactions within surface materials that create new mineral phases found nowhere else. The combination of extreme temperatures and high-energy radiation creates conditions where familiar minerals undergo transformations that push the boundaries of solid-state chemistry. Some of these thermally processed materials develop crystalline structures that exist only under Mercury's unique environmental conditions. Mercury's extreme orbital characteristics have created feedback loops between its surface composition and its atmospheric dynamics that operate on geological timescales. As certain minerals break down under intense thermal cycling, they release volatile elements that contribute to the planet's exosphere. These atmospheric additions then influence how solar radiation interacts with the surface, potentially altering the rates of thermal breakdown and creating complex chemical cycles that span millions of years. The study of how Mercury's orbital extremes influence its geological evolution has revealed processes that challenge conventional models of planetary development. Rather than following a simple cooling and stabilization pattern like other terrestrial worlds, Mercury undergoes ongoing thermal processing that continuously modifies its surface composition and internal structure. The planet serves as an example of how extreme orbital environments can drive geological activity that persists for billions of years. The electromagnetic phenomena generated by Mercury's orbital motion through the solar wind create particle acceleration mechanisms that exist nowhere else in the inner solar system. During perihelion passages, the interaction between Mercury's magnetic field and the compressed solar wind generates electric fields powerful enough to accelerate atmospheric particles to velocities approaching significant fractions of the speed of light. These particle acceleration events create radiation bursts that represent some of the most energetic processes occurring on any terrestrial planet. Mercury's extreme orbital environment has also influenced its thermal evolution in ways that affect its long-term geological stability. The constant addition of tidal heating energy helps maintain higher internal temperatures than would be possible through radioactive decay alone, keeping portions of Mercury's core molten long after they should have solidified. This thermal input creates internal dynamics that continue to drive geological processes billions of years after other terrestrial planets became geologically inactive. The precision required to predict Mercury's orbital behavior under these extreme conditions has pushed the boundaries of computational astronomy and theoretical physics. The planet's motion involves so many interacting forces operating at their theoretical limits that modeling its long-term orbital evolution requires some of the most sophisticated calculations ever attempted in planetary science. These computational challenges have driven advances in numerical methods that have applications throughout astronomy and physics. Perhaps most remarkably, Mercury's extreme orbital characteristics have made it a natural laboratory for studying how planetary systems behave when pushed to their absolute limits. Every aspect of Mercury's environment, from its surface geology to its magnetic field dynamics, operates under conditions so extreme that they provide unique insights into the boundaries of planetary physics. The ongoing study of Mercury's orbital extremes continues to yield surprises about both the planet itself and the fundamental processes that govern planetary behavior. Each perihelion passage provides new opportunities to observe how extreme gravitational and thermal environments affect planetary systems, while each aphelion retreat offers chances to study how these systems recover from maximum stress conditions. As Mercury continues its eternal orbital dance, swinging between the blazing intensity of close solar approaches and the relative calm of its more distant phases, it carries with it the distinction of being not just the most extreme planet in our solar system, but also one of the most scientifically revealing. The planet's orbital characteristics create a natural laboratory where the most fundamental forces in the universe operate at their observable limits, providing insights that extend far beyond planetary science to touch the deepest questions about the nature of matter, energy, and space-time itself. The extreme orbital environment that defines Mercury's existence serves as both the source of its extraordinary characteristics and the key to understanding how planetary systems can evolve under the most challenging conditions imaginable. In studying Mercury's orbital behavior, we glimpse not just the mechanics of planetary motion, but the intricate dance between gravity, thermal physics, and electromagnetic forces that shapes worlds throughout the universe. This remarkable planet's orbital story demonstrates how extreme conditions can reveal hidden aspects of familiar physical processes, making Mercury an indispensable component of our quest to understand how the universe operates when pushed to its absolute limits. As the most extreme world in our solar system, Mercury continues to challenge our assumptions about what's possible when matter and energy encounter the most demanding environments that nature can create. The extreme conditions that define Mercury's existence extend beyond what we can observe directly from our distant vantage point. This remarkable world operates as a cosmic laboratory where the fundamental forces of nature interact under circumstances so intense they reshape our understanding of planetary science itself. Every measurement we take, every observation we make from orbiting spacecraft reveals new layers of complexity in how this small world manages to maintain its extraordinary characteristics while enduring punishment that would destroy any other terrestrial planet. Consider the sheer violence of Mercury's daily existence. As the planet rotates through its 58 Earth-day cycle, different regions experience thermal shocks so severe it would shatter most materials we know. The transition from blazing daylight to frigid darkness doesn't occur gradually as it does on Earth. Instead, Mercury's surface materials must endure temperature changes that span more than 1100 degrees Fahrenheit within the space of just a few hours. This thermal whiplash creates stresses within surface rocks that exceed the breaking point of granite, constantly fracturing and refracturing the planet's outermost layers. The electromagnetic environment surrounding Mercury pulses with energies that dwarf the most powerful phenomena we experience on Earth. During solar storm events, when our sun unleashes coronal mass ejections and solar flares, Mercury receives the full brunt of these cosmic hurricanes with no atmospheric protection whatsoever. The charged particles in these storms strike Mercury's surface with such intensity that they actually knock atoms loose from the rocky terrain, creating brief but spectacular displays as liberated sodium and potassium atoms glow briefly before escaping to space. These particle bombardment events occur with such regularity that they've become an integral part of Mercury's geological processes. Rather than simply eroding the surface, as might happen on a less extreme world, the constant particle impacts drive chemical reactions that create new mineral phases. Some regions of Mercury's surface show evidence of having been completely chemically altered by billions of years of high-energy particle processing, transforming familiar rock types into materials that exist nowhere else in the solar system. The magnetic field interactions that occur around Mercury create phenomena so exotic they challenge our understanding of planetary magnetism. The planet's weak but persistent magnetic field channels solar wind particles into complex spiral patterns that create natural particle accelerators in the space surrounding the world. These acceleration zones boost charged particles to velocities so extreme that when they finally impact Mercury's surface, they carry energies equivalent to cosmic radiation from deep space. The thermal extremes that Mercury endures have created a form of planetary metabolism where the world literally breathes materials in and out with each rotation cycle. During the scorching day, surface minerals decompose and release volatile elements that escape into the tenuous atmosphere. As night falls and temperatures plummet, some of these same elements condense back onto the surface in different locations, creating slow but continuous material transport across the planet's landscape. This thermal breathing process has been operating for billions of years, gradually redistributing materials across Mercury's surface in patterns that reflect the planet's complex thermal environment. Regions that experience the most extreme heating show chemical signatures that differ dramatically from areas that remain in permanent shadow, creating compositional maps that directly mirror the planet's thermal geography. The gravitational environment that Mercury inhabits subjects the planet to tidal forces so intense they actually deform the solid surface by several meters twice during each orbital cycle. These tidal bulges move across Mercury's landscape like slow-motion waves, creating stress fields within the planetary crust that trigger seismic activity deep beneath the surface. Some scientists speculate that this ongoing tidal flexing might contribute to volcanic activity that continues to reshape portions of Mercury's interior. The interaction between these tidal forces and Mercury's extreme thermal cycles creates geological processes that operate according to principles unknown elsewhere in the solar system. As surface materials expand and contract with temperature changes, while simultaneously being flexed by tidal forces, they undergo complex deformation patterns that can create entirely new types of geological structures. Some regions show evidence of materials that have been stretched, compressed, heated, and cooled so many times that they've developed crystalline structures found nowhere else. The atmospheric dynamics around Mercury operate in ways that defy conventional meteorology. Without substantial atmospheric mass to create traditional weather patterns, Mercury's exosphere responds directly to electromagnetic and thermal forces in ways that create phenomena resembling aurora displays, but occurring in wavelengths invisible to human eyes. These electromagnetic light shows pulse and flicker with the rhythm of solar wind variations, creating atmospheric displays that exist nowhere else in the inner solar system. The chemical processes occurring within Mercury's tenuous atmosphere involve reaction pathways that exist only under the planet's extreme conditions. The combination of intense ultraviolet radiation, high-energy particle bombardment, and extreme temperature variations creates a chemical laboratory where familiar elements combine and recombine in ways that push the boundaries of atmospheric chemistry. Some of the molecular species detected in Mercury's exosphere exist for only brief moments before being broken apart by the harsh radiation environment. And so, as we drift toward the end of our cosmic journey together, we find ourselves forever changed by what we've discovered about this extraordinary world. Mercury stands as testament to the universe's capacity for extremes, a small planet that challenges every assumption we might hold about the limits of planetary endurance. From its scorching days that could melt metal to its frozen polar shadows harboring ancient ice, from its actively forming hollows to its mysteriously powerful magnetic field, Mercury continues to rewrite the boundaries of what we thought possible in our solar system. Sweet dreams, fellow cosmic travelers, and remember that even in the most extreme corners of our universe, wonder and beauty persist in ways that forever expand our understanding of existence itself.